Home malware analyzing C++ runtime library code tampering and software supply chain attacks by Mohammed Mukbel. For the past few years, the security industry's very backbone, its key software and server components, has been the subject of numerous attacks through cybercriminals' various works of compromise and modifications. Such attacks involve the original softwares being compromised via malicious tampering of its source code, its update server, or in some cases, both. In either case, the intention is to always get into the network or a host of a targeted entity in a highly inconspicuous fashion, which is known as a supply chain attack. Depending on the attacker's technical capabilities and stealth motivation, the methods used in the malicious modification of the compromised software vary in sophistication and astuteness. 4 major methods have been observed in the wild: the injection of malicious code at the source code level of the compromised software, for native or interpreted just-in-time compilation-based languages such as C++, Java, and .NET, the injection of malicious code inside C++ compiler runtime, CRT, libraries, for example, poisoning of specific C runtime functions. Other less intrusive methods, which include the compromise of the update server such that instead of deploying a benign updated version, it serves a malicious implant. This malicious implant can come from the same compromised download server or from another completely separate server that is under the attacker's control. The repackaging of legitimate software with a malicious implant. Such Trojanized software is either hosted on the official yet compromised website of a software company or spread via BitTorrent or other similar hosting zones. This blog post will explore and attempt to map multiple known supply chain attack incidents that have happened in the last decade through the 4 methods listed above. The focus will be on Method 2, whereby a list of all poisoned C++ runtime functions will be provided, each mapped to its unique malware family. Furthermore, the ShadowPad incident is taken as a test case, documenting how such poisoning happens. Methods 1 and 2 stand out from the other methods because of the nature of their operation, which is the intrusive and more subtle tampering of code. They are a category in their own right. However, Method 2 is far more insidious since any tampering in the code is not visible to the developer or any source code parser. The malicious code is introduced at the time of compilation/linking. Examples of attacks that used a combination of methods 1 and 3 are, the Trojanization of MediaGet, a BitTorrent client, via a poisoned update, mid-February 2018. The change employed involved a malicious update component and a Trojanized copy of the file MediaGet.exe. The Nitya/Medoc attack on Medoc, an accounting software by Intellect Service, which delivered the destructive ransomware Nitya/NotPetya by manipulating its update system, April 2017. The change employed involved backdooring of the .NET modules fit published objects.dll, the Kingslayer attack on Event ID, which resulted in the compromise of the Windows Event Log Analyzer software's source code, service executable in .NET, and update server, March 2015. An example of an attack that solely made use of Method 3 is the Manju Incident, which involved the compromise of the update server for the media player GOM player by GimLab and resulted in the distribution of a variant of GH0SD-RAT towards specific targets, December 2013. For Method 4, we have the HAVEX incidents, which involved the compromise of multiple industrial control system, ICS, websites and software installers, different dates in 2013 and 2014. Examples of attacks that used a combination of methods 2 and 3 are, Operation Shadowhammer, which involved the compromise of a computer vendor's update server to target an unknown set of users based on their network adapter's media access control, MAC, addresses, June 2018. The change employed involved a malicious update component. An attack on the gaming industry, Winty A, which involved the compromise of 3 gaming companies and the backdooring of their respective main executables, publicized in March 2019. The Cleaner case, which involved the compromise of Piriform, resulting in the backdooring of the Cleaner software, August 2017. The ShadowPad case, which involved the compromise of NetSaron Computer Incorporated, resulting in the backdooring of all of the company's products, July 2017. The change employed involved malicious code that was injected into the library in Secur.dll, which was used by all of the company's products. Methods 2 and 3 were also used by the Windy Group, which targeted the online video game industry, compromising multiple companies' update servers in an attempt to spread malicious implants or libraries using the headlib tool. 2011. Another example is the Xcode Ghost Incident, September 2015, in which Apple's Xcode Integrated Development Environment, IDE, and the compiler's core services Mako object file were modified to include malware that would infect every iOS app built, via the linker, with the Trojanized Xcode IDE. The Trojanized version was hosted on multiple Chinese file-sharing services, resulting in hundreds of Trojanized apps landing on the iOS App Store unfettered. An interesting case that shows a different side to the supply chain attack methods is the Event Stream incident, November 2018. Event Stream is one of the widely used packages by NPM. Node.js Package Manager, a package manager for the JavaScript programming language. A package known as FlatMap Stream was added as a direct dependency to the Event Stream package. The original author/maintainer of the Event Stream package delegated publishing rights to another person, who then added the malicious FlatMap Stream package. This malicious package targeted specific developers working on the release build scripts of the Bitcoin wallet AppCopay, all for the purpose of stealing Bitcoins. The malicious code got written into the app when the build scripts were executed, thereby adding another layer of convertness. In most supply chain attack cases that have been happening for almost a decade, the initial infection vector is unknown or at least not publicly documented. Moreover, the particulars of how the malicious code gets injected into the benign software codebase are not documented either, whether from a forensics or a tactics, techniques, and procedures (TTP) standpoint. However, we will attempt to show how Method 2, which employs sophisticated tampering of code and is harder to detect, is used by attackers in a supply chain attack, using the ShadowPad case as our sample for analysis. An in-depth analysis of Method 2, case study, ShadowPad. There are subtle differences and observations between tampering with the original source code, as in Method 1, and tampering with the C++ runtime libraries, as in Method 2. Depending on the nature and location of the changes, the former might be easier to spot, whereas the latter would be much harder to detect if no file monitoring and integrity checks had been in place. All of the reported cases where the C++ runtime libraries are poisoned or modified are for Windows binaries. Each case has been statically compiled with the Microsoft Visual C++ compiler with varying linker versions. Additionally, all of the poison functions are not part of the actual C++ standard libraries, but are specific to Microsoft Visual C++ compiler runtime initialization routines. Table 1 shows the list of all known malware families with their tampered runtime functions. Malware family poisoned Microsoft Visual C++ runtime functions shadowhammer_crt exit process uint exit code, / exits the process. Checks if it's part of a managed app / it is a CRT wrapper for exit process gaming industry, hacked app, Winty. A_scrt_common_main_ say void / point of the C runtime library, _main startup, with support for structured exception handling which calls the program's main function cleaner stage 1, _scrt_common_main_ say void stage 2. Greater than dropped 32-bit, _security _init _cookie stage 2, greater than dropped, 64-bit, _security _init _cookie void _security _init _cookie void, / initializes the global security cookie / used for buffer overflow protection shadowpad _init term _pvfv begin. _pvfv fend, / call entries in function pointer table / the entry, 0 by 1000d600, is the malicious one. Table 1, list of poison / modified Microsoft Visual CRT functions in supply chain attacks. It's the linker's responsibility to include the necessary CRT library for providing the startup code. However, A different CRT library could be specified via an explicit linker flag. Otherwise, the default statically linked CRT library lib.lib, or another, is used. The startup code performs various environment setup operations prior to executing the program's main function. Such operations include exception handling, thread data initialization, program termination, and cookie initialization. It's important to note that the CRT implementation is compiler, compiler option, compiler version, and platform specific. Microsoft used to ship the Visual C runtime library headers and compilation files that developers could build themselves. For example, for Visual Studio 2010, such headers would exist under Microsoft Visual Studio 10.0/VC/CRT, and the actual implementation of the shadowpad poison function _init term would reside inside the file crt0dat.c as follows. All comments were omitted for readability purposes. This internal function is responsible for walking a table of function pointers, skipping null entries, and initializing them. It's called only during the initialization of a C++ program. The poison DLL and Secur.dll is written in the C++ language. The argument begin points to the first valid entry on the table, while fend points to the last valid entry. The definition of the function type _pvfv is inside the CRT file internal.h. The above function is defined in the crt0dat.c file. The object file crt0dat.obj resides inside the library file lib.lib. Figure 1 shows shadowpad's implementation of _init term. Figure 1. Shadowpad poison _init term runtime function. Figure 2 shows the function pointer table for shadowpad's _init term function as pointed to by begin and fend. This table is used for constructing objects at the beginning of the program, particularly for calling C++ constructors, which is what's happening in the screenshot below. Figure 2. Function pointer table for shadowpad poison _init term runtime function as shown in Figure 2. The function pointer entry labeled malicious _code at the virtual address 0x1000 F6A0 has been poisoned to point to a malicious code, 0x1000 E600. It's more accurate to say that it is the function pointer table that was poisoned rather than the function _init term. Figure 3 shows the cross-reference graph of the _init term CRT function as referenced by the compiled shadowpad code. The graph shows all call paths, reachability, that lead to it, and all other calls it makes itself. The actual call path that leads to executing the shadowpad code is DLL entry point, greater than _lamain startup, greater than _CRT_init, greater than _init term, greater than _imp _init term, greater than malicious _code via function pointer table. Figure 3. Call cross-reference graph for shadowpad poison _init term runtime function. Note that the internal function _init term is called from within the CRT initialization function _CRT_init, which is responsible for C++ DLL initialization and has the following prototype. One of its responsibilities is invoking the C++ constructors for the C++ code in the DLL and Secur.dll, as demonstrated earlier. The said function is implemented inside the CRT file crt_dll.c, greater than object file crt_dll.obj, greater than library file msv_crt.lib. The following code snippet shows the actual implementation of the function _crt_init. So, how could an attacker poison any of those CRT functions? It's possible to override the original benign lib.lib/msv_crt.lib library with a malicious one, or modify the linker flag such that it points to a malicious library file. Another possibility is by hijacking the linking process such that as the linker is resolving all references to various functions, the attacker's tool monitors this process, intercepts it, and feeds it a poison function definition instead. The backdooring of the compiler's key executables, such as the linker binary itself, can be another stealthy poisoning vector. Conclusion: although the attacks for Method 2 are very low in number, difficult to predict, and possibly targeted, when one takes place, it can be likened to a black swan event. It will catch victims off guard and its impact will be widespread and catastrophic. Tampering with CRT library functions and supply chain attacks is a real threat that requires further attention from the security community, especially when it comes to the verification and validation of the integrity of development and build environments. Steps could be taken to ensure clean software development and build environments. Maintaining and cross-validating the integrity of the source code in all compiler libraries and binaries are good starting points. The use of third-party libraries and code must be vetted and scanned for any malicious indicators prior to integration and deployment.